So today we're going to be looking at the dot product. And the dot product is a concept in linear algebra, which is what happens when we multiply two matrices together. One of the things that the dot product needs before we can even begin taking it is we need to check to make sure that the matrix is eligible to find the dot product. Now, this is typically shown as we find the dimensions of a matrix. So for the example given, we know this is a 3-row by 2 column, so 3 by 2, and this is a 2-row by 3 column, so a 2 by 3. If the, row by column, if we have the columns of the first one match the rows of the second one, so columns matches rows, we can take the dot product. The resulting matrix will be a 3 by 3, and a different way to look at that is to look at visually what's going on. Similar to distribution, we're going to take that first row and multiply it times both of the numbers in the column. So I have to have a 2 by 2, which is why these two numbers need to match. If I have 2 entries, so 2 columns in my first one, I have to have 2 rows in my second one. The other concept is that order matters. If I take matrix A and multiply it times matrix B, it is not the same as B times A. We notice that this row is by this column. I'm not multiplying this row by this column. Those are two completely different sets of numbers. So the order when we multiply matrices matters. So let's go ahead and take a look at, can we find the dot product in some of these examples? So let's go ahead and let's zoom in on some of them. So for number 1, let's go ahead and label what the dimensions are. Remember, we list rows by columns. So in this case, it is a 1-row by 2 column. Here I have a 2-row by 1 column. And again, what we're checking for is we're checking to see, do the inside numbers match? So can a dot product be found? Yes. If so, what are the dimensions? Well, the dimensions will be a 1 by 1. Our matrix will basically be reduced down to a scale factor. So if we look at something right beside it, let's take a look at this one. Okay, so this one we're looking at rows by columns. So I have a 2-row by 1 column. And here I have a 1-row by 2 column. So again, what I've got going on here is I'm checking to make sure that if I were to take the dot product, will this row match up with this column? Yes, I have a 1-to-1. That works out fine. So I can take the dot product of this. If so, what are the dimensions? Well, the dimensions will be a 2 by 2 matrix. Perfect. So if I look at the next one, what I've got going on here is rows by columns. I have a 2 by 2. In this, I have a 2 rows by 1 column. Again, we're checking to see if I were to take the dot product, do each one of my elements in my row match up with an element in the column? Yes. So I can take the dot product here, and my answer will be a 2 by 1 matrix. Perfect. If I look at number 6, let's take a look at this. So rows by column, I have 2 rows by 1 column. And here I have a 2-row by 2 column. And here, unfortunately, what we notice is the fact that if I were to try to take the dot product here, I would multiply this 5 times the 1, but I don't have a second number to multiply times the 4. So the dot product cannot be found. No matter how hard I would like to do this, I can't, because I can only take the dot product of the 5 and the 1. I don't have a second element to multiply times the 4. So why don't you go ahead and try these two and see what you get. Okay, so let's take a look. So here I have 3 rows by 2 columns, and here I have 2 rows by 1 column. Albeit these look very mismatched, this works perfectly fine because I have each one of these elements, the 8 and the -1, can be multiplied by the -5 and the 2. Everything matches up. My resulting matrix will be a 3 by 1. If I flip it, let's see, my rows here are going to be 2 by 1. And over here, my rows are 3 by 2. The problem with this is if I try and take the dot product, I'm going to take this 5 and I'm going to try and find the dot product with this column. The 5 pairs up evenly with the 8, but I don't have two other elements to pair up with the 7 and the 1. So I can't do anything. So there we go. So the top portion is just about, can we do it? So the next part is what we're going to look at. On number 13, we're going to state each matrix, what we can multiply. So what we're going to do is we're going to go through each one of these and we're going to list the dimensions. So this is a 1 by 2. This is a 2 by 1. This is a 2 by 2. This is a 2 by 3. And this is a 3 by 2. And in essence, what we're going to do is we're going to go through and we're going to pair up A with everything that has a 2 for the number of rows. So I know that A can be paired up with B. A can also be paired up with C. And A can be paired up with D. It can't be paired up with E because if I had 2 elements, I have 3 in this column, those won't match. Additionally, if A was paired up with B, I would get a 1 by 1. If A was paired up with C, I would get a 1 by 2. And A with D, I would get a 1 by 3. Okay. Let's go through and list what B would be compatible with. Now with B, I'm looking for any matrix that has 1 row. So B can be paired up with A, and that's it. That's the only one that they can pair up with. And now the resulting matrix with this will be if B is paired with A, I'll have a 2 by 2. And again, what we see here is we see our first instance of order mattering. A times B will result in a 1 by 1 matrix, but B times A will result in a 2 by 2 matrix. Even though these look like something that in regular algebra we can interchange, A times B, B times A, when we deal with linear algebra and matrices, they produce two very distinct outputs. So let's go ahead and pair up C with everything we can. Now C, we're looking for, again, anything with 2 rows. So I can pair it up with either B or D. So B or D can be paired up with C. So if I paired up B with this, I would say, okay, my inside numbers match. I would have a 2 by 1. If I paired it up with D, I would have a 2 by 3. Perfect. And so let's go ahead, pause the video, see if you can't figure out which matrices D and E can be paired with. Unpause the video when you're done and see all you did. Okay, so what we're looking at is D. We're looking at any matrix with 3 rows. So D only has one option, E. And that will produce a 2 by 2 matrix. E, we're looking for any matrix that has 2 rows. So I have 3 options, B, C, and D. So B, C, and D, E can be multiplied by. If E is multiplied by B, it will be a 3 by 1. If E is multiplied by C, it will be a 3 by 2. And if E is multiplied by D, it will be a 3 by 3. Awesome. And then one of the things that it also does ask is it says explain why. Remember, when we find the dot product, each element of the row must match with each element of the column in order to be multiplied and summed. So the 1 and the 3, the 2 and the 4, I have the same amount of elements. If I had something like this, I would have 1, 2 paired up with 1, 2, 3, I would have a mismatch. So the row must have the same number of elements as the column of the following matrix. That's the only way that we can multiply the two together, because that's the only way we can find the dot product. And so that's a nice little intro, which will bring us to our next set of problems. And now our next set of problems are going to be finding dot products of these matrices. We're not multiplying the two matrices together just yet. We're finding the dot products of specific parts of this problem or of this process. So starting off with number 14, if we look at this, we know I'm going to find the dot product of row 1 and column 1. So I'm going to call that matrix A, and I'm going to call this matrix B. So remember, we want to find each element of row 1. So I'm going to say, okay, this will be a 3 and a 1. So I'll have a 3 and a 1. And I'm multiplying it times each element of this column. I was going to draw on these, but we've got a few others to go for here. So column 1 is going to be a 4 and a 2. So I'm going to multiply those together, and I'm going to sum it up. So what I have is I have a 3 by 4, which is going to be a 12 plus 2. The dot product of row 1, column 1 is going to be 14. Perfect. So if I go for part B, I'm doing row 1 with column 2. I'm doing it for the next column over. So what I'm going to do is I'm going to say each element of row 1. So I have a 3 and a 1, and I'm multiplying it times each element of column 2. So times 0 times 1. And I'm going to add them together. So 3 times 0 is 0, plus 1. The dot product of row 1 and column 2 is going to be 1. Perfect. So then if I go to C and D, what I want you to do is I want you to pause the video, unpause it when you're done, and see how well you do with finding the dot products of row 2 and column 1, and then row 2 and column 2. Okay, so let's see how we did here. So I've got row 2, so I have 5 and 6, and I'm multiplying it times column 1, which is going to be times 4 and times 2. When I'm done with that, I'm going to add up those values. So this is going to be a 20 plus 12, which is a 32. Same thing with part D. I'm going to take each element of row 2, a 5 and a 6, and I'm going to multiply it times each element of column 2. So times 0 times 1. Once I've done that, I'll add them together. So 5 times 0, 6 times 1, 6. Awesome. What we've unknowingly done with these 4 things is we've actually found the resulting matrix. Because we found the dot product of each row with each column, row 1 with both columns, right here and right here, row 2 with both columns, the resulting matrix that this will produce if I take A times B will be a 14, 1, 32, and 6 matrix. So conveniently, we know the answer to this. But don't worry, we'll be covering this in a later section. Let's pop off to number 16. So number 16 is a 3 by 3 and a 3 by 3 matrix. So albeit we might be doing some of the same functions, row 1 and column 1, there's going to be more entries involved. But the process works exactly the same. Just to keep things easier to figure out, I'm going to label this as A and this as B. So for part A, what I'm going to do is I'm going to take each aspect of row 1, 8, 12, and negative 3, 8, 12, and negative 3, and I'm going to multiply it times each aspect or each element of column 1. So times 1, times 0, times 0. And when I'm done with that, I'm going to add them all together. You'll notice that adding a negative is basically just going to be subtracting here. So 8 times 1 is going to be 8 plus 0 plus 0, which means the dot product of row 1 and column 1 is 8. I do the same thing for part B with row 2, column 2. I'm going to take row 2. Each element of it is going to be a 1, a 5, and a negative 9. I'm going to multiply it times each element of column 2. So times 0, times 1, times 0. Once I figured that out, I'm going to add them all together. So 0 plus 5 plus 0. So the dot product of row 2, column 2 is 5. So what I want you to try is I want you to try C and D on your own. Pause the video, unpause it when you're done, and see how well you did. Okay, so let's see how we're doing here. I have row 2 in column 3, so I'm going to take row 2, which is going to be a 1, a 5, and a negative 9, multiply those times column 3, which is times 0, times 0, times 1, and I'm going to add them together. So 0 plus 0 minus 9, which results in a negative 9. So the dot product of row 2, column 3 is negative 9. If I try it with row 3, column 2, I'm going to do row 3. In this case is 6, 4, and 10. And I'm going to multiply it times column 2, which is going to be times 0, times 1, times 0. And I'm going to add them together. 6 times 0, 4 times 1, 10 times 0, 4. Perfect. And there we go.